Hello, I'm Mr. Day, and today we're going to talk about levers. All right, there are three types of, or classifications of levers. All right, the first thing you need to know about levers is it has a fulcrum. A fulcrum is just the point at which a lever pivots. All right, and I'm going to show you as I go through them. So your first class of lever is basically, if you've ever seen a seesaw, that's what it is. So the actual definition is when a fulcrum is between effort force and resistance force. So here, if I say my effort force is here, my resistance force is here, because that is what makes this a first class lever. The fulcrum is in between those two. And this is the fulcrum. This is just the pivot point. Alright, so if my effort is here, my resistance is over here. So say I have 100 pounds over here and I need to push it up, my effort's going to go here to resist it. If I pick it up from over here, that is something completely different. That's a different lever. So a seesaw is a good example. Let me show you another drawing of it. So if you actually have kids on a seesaw, my little stick figures on it. So ask yourself, which one now, by the definition, is the effort force and which one is the resistance force? So this one right here is the effort force. Over here is the resistance force. So a seesaw is usually the one, the big example of a first class lever. Now we're going to move on to the second class lever. This is your second class lever. It is when the resistance force is in between the effort force and the fulcrum. So I didn't explain this before, and I'll actually read you the definition. So an effort force is the force applied to a simple machine. So effort, put an effort to something, you're putting in a force. So the resistance force is a force the machine applies to overcome resistance. So resistance is just what's stopping you from doing it. So if I go push against the wall, that's the resistance force. That is not for a lever, but I'm just telling you, basically, that's what it would be. All right, so now we have the fulcrum. So an example of this would be, the biggest example of this is a wheelbarrow. So you have your person here. I should probably give them a body. Pushing a wheelbarrow. I don't know why they're looking up at the sky, but they are. So here is your fulcrum. Here is your resistance. I'm just going to write RF, and here is your effort force. All right? So that is your biggest one here. So it goes fulcrum, resistance force, effort force. The first class lever went resistance force, fulcrum, effort force. All right? So now we're going to move on to our third classification. All right, our third classification of lever is this. So I have my fulcrum, effort force, and resistance force. This is usually the hardest one for people to think of because you've looked at the other two and you kind of understand it. This is probably my least favorite. If you grew up around snow, shoveling snow is the worst thing when you're getting woke up every 30 minutes because there's a blizzard outside and you have to make sure that the snow is gone by the morning. You know what I'm talking about. It is terrible. So here we go. This person is out at 2 o'clock in the morning because their parents just woke them up because there's snow everywhere and it's negative 20 degrees outside. I'm a little salty about it if you can't tell. All right, so this is your resistance force right here. This is your effort force. And here's your fulcrum. Your little body right here. All right? And basically, so So shoveling is basically the example of a third-class lever. If you've never had to shovel snow, lucky you. All right, and those are the three classifications of lever. Now I'm going to talk about torque and what that means for levers. All right, torque. All right, so I drew this whole big thing to confuse you. It's not actually that confusing, but what this is clockwise and counterclockwise. You have your distance for the counterclockwise, or counterclockwise, yeah. And then you have your distance for clockwise. So just split it in two. This side's your clockwise, this side's your counterclockwise. If this entire thing is flat and balanced, that means your counterclockwise and your clockwise will be equal. The force will be equal. All right? So now I'm going to do an example to sort of show you this when one side's greater than the other side and when they're balanced. All right, so the first one we're gonna do is we're gonna figure out how much torque is there for your counterclockwise. All right, so I'm gonna say, and I wrote my silly formula up there. So what's my torque for my counterclockwise? So that's my force, which is 80, times my distance, which is just 1. So the amount of torque I'm putting on the counterclockwise side is just 80 newtons meters. All right, now let's find it for your clockwise. So your torque of your clockwise is your force, which is 100, times 0.5, which is your distance. You get your torque is 50 newtons meters. That newtons meters is your thing for it. So if I were to say now that I found my torque for my counterclockwise and then my torque for my clockwise. So if you look at a watch, look at the watch on. That's clockwise, is counterclockwise. Is this balanced? 50 newtons per meter, 80 newtons meters. No, it is not balanced because they are not equal to each other. So you'd have more force going over here, so this would get pushed down a little bit more than the other side. All right, if they equal each other, that means they are balanced. So in this case, this is actually going to rotate counterclockwise. So say I switch this up and I make this 20 newtons of force over here. So 20 times 1 gives me 20 newton meters. So is this balanced? No, it is not. So now it's going to rotate clockwise, right? Whichever side has the greater torque is the way it's going to rotate. So now if I made this 50, and I know some of you OCD people are just being driven crazy right now by me just erasing this stuff, but that's all right. So now it's 50 newton meters, 50 newton meters. It's balanced, so it's just going to sit there. All right, so it's always just the force times the distance, and force times the distance. If it's going to be balanced, it would be your force times your distance. So clockwise equals, we'll call it counterclockwise actually. Then your force times your distance of the clockwise. If it's balanced, those will equal each other. And that is levers and torque. I hope this helped out, and good luck.